Hello everyone and welcome back to Thermojov channel. In this video, we are going to learn how to determine the thermodynamic phase of a refrigerant and how to find its properties using thermodynamic tables in engineering equation solver. We will go through this two famous property diagram, TV and PV, and we can discuss regarding this one. But this is the example we are going to identify its question. Actually, this is related to the refrigerant R134a. We are going to determine the specific heat and specific enthalpy of this refrigerant at two given temperature and pressure. Temperature is 90 degrees Celsius and pressure is 200 kilopascal. So first, we are going to determine the thermodynamic phase of this refrigerant. Let's first go through these two diagram, TV and PV. As you can see here, we have two line here, saturated liquid line and saturated vapor line. Based on these two lines, we have three separate and different region, compressed liquid, saturated liquid vapor, and finally superheat vapor regions. So we have these three main regions in both of these two TV and PV diagrams. For TV diagram, we usually use this pressure constant line. So on this line, for example, the pressure from here till here is P2 and is almost and always constant. So that because of that, we call this line as a constant pressure line. And in this TV diagram also, we can say that this P2 is always greater than the P1, and this is another constant line for pressure. We will go into EES and see some of this example there. And for the PV diagram, all these regions and lines are the same. The only thing is we instead of having constant pressure line, we have a constant temperature line. For example, this is T2, which is a constant temperature. So if we move on this line, the temperature is always constant and equal to T2, and this T2 is always greater than the T1. Now let's go and find if this working fluid R134a is in a saturated region or like a superheated region. So to find out, first we need to know what is saturated state. Actually, saturated state is a special condition where the refrigerant is just about to change phase. At this point, temperature and pressure are not independent properties. Once one of them is specified, the other is fixed automatically according to the saturation properties of the fluid. For example, here, if this refrigerant is in the saturated phase and its temperature is 90 degrees Celsius, so its pressure should be this value always, 3246. But for our problem, it is 200 kilopascal, so which is less than much less than this value. So how should we identify this is a so for sure we know it is not in the saturated area. So we can now go and find out if it is in the superheat or compressed liquid. Now let's go and find out if this fluid is in superheat region or in compressed liquid region. We can discuss about this one. So for example, I can just actually bring this picture here and discuss regarding this value. So actually, according to this table, if the temperature is 90, the saturated pressure will be 3246. So based on that, I can go here and I can draw one line, for example, like this, I can use this red line, and then if I actually, let me draw a line like this. If we consider this one as T 90 degrees Celsius, so here we have this temperature, and as we know, this pressure here is our saturated pressure, and the pressure is 3200 for the 6 kilopascal. But in our problem, the pressure is less. So we need to find out, so if this is this line, so we need to have another constant pressure line related to 200 kilopascal. So this one should be under this line. And if I consider this line as a pressure of 200 kilopascal, so for this temperature, as you see, 90 degree, and for this lower pressure we have here. So we are in this region, and this region is related to superheated vapor region. So we can simply find out that this data for this refrigerant actually is related to the superheated vapor region. So here the temperature is 90 degrees Celsius, and then the pressure is 200 kilopascal according to the data for the saturated pressure. And that's because this pressure, saturated pressure and temperature are dependent to each other in this region, saturated vapor. So once one of them is specified like this, the other is fixed automatically according to the saturation properties of the fluid. So I need to determine actually the specific volume and a specific enthalpy. I need to go to the superheat table, which is this table. This is related to the superheated refrigerant of R134a. So in this table, we need to find out the proper temperature and also pressure. So here, as you can see, the temperature here, let me go back again here. The temperature is 90 degrees Celsius, and the pressure is equal to 200 kilopascal or 0.2 megapascal here. So according to this one, if I go here, so this is related to the specific volume, and this is a specific enthalpy. So we can actually check this one in the EES software. So let me go directly to the EES software. So the first thing you should know is this table, this graph here. So here you have access to the property plot of different refrigerant and different material here. So here you see there it's a list for many of the refrigerant that you have access to all the data here. And so because of this example, I need to select this refrigerant 134a. And then here you can select and define different constant line if you are going to draw the PV or, for example, TV diagram. In this case, for example, I'm going to draw the PV diagram. Then these are the constant line that you can actually define on this property plot. For example, I can just simply press OK, and as you can see here, you have this property plot here for this refrigerant and for this constant temperature that we determined there. Okay, so now let me draw one more of this property, but this time I'm just going to select two constant value. So the first constant temperature is our 90, or I can just draw the TV this time, and I can just draw some two constant line. One is this 3246, which is related to saturated pressure, and this one I can call it as 200, and all of these are on kilopascal. So then I can draw these two lines and then make it a little bit bigger. So just make it fit here. Then as you can see, this is this property diagram, temperature TV actually diagram, and these are those two constant pressure line. And as you can see, this pressure for this 90 degrees Celsius, as you can see, just let me first so I can just double click here and activate this grid line. So now I have this grid line, and as you can see, this is related to 90 degrees Celsius. You can also activate this first. Let me activate this minor line actually here. So this line is, as you see, related to 90 degrees Celsius, this one. And as you can see, the saturated pressure, this is the constant pressure line, as you can see here. You can also even change the size and put some symbol on this one. And then for the other line, P equal 200, you can select another line and color. So this is 200, and this is actually 3246. So if we consider this one as a 90 degrees Celsius, and this is the saturated pressure for this temperature, and this is, as you can see, dependent to this 90 degrees Celsius. So for our case, for this 90 degrees Celsius, if you see this constant pressure line, this red one, is connected to this temperature 90 degree here in this area, and this area is related, as we discussed, related to the superheated region. So now we can understand we are in the superheated region, and based on this one, you can just simply go here and bring down here and then find this specific volume. But we are not going to find out through the diagram. We can just simply go here and then use the library of the EES software and find out these two specific volume and a specific enthalpy. And now we can simply define the specific heat. There's a video you can find out how we can define this Greek letter in the EES. I can write it new here, and then here we can go to this function information and go to the thermophysical properties, and then find out the refrigerant that you are going to find out the data for it. So we will go to the refrigerant 134a. We can select it, and then here you can find out all the information related to your refrigerant. So here I can scroll down, and then at the end of the list I can find out the specific volume, cubic meter per kilogram. So I can just simply select it, and then you can copy and paste here, or just simply paste here, and then I can write it down. Before that, I can define the temperature. So I can write it as T1, for example, is equal to 90 degree, and then P1 is equal to 200 kilopascal. And for the units, you can go to this actually preference here and find out this is SI unit. Pressure is on kilopascal, and then temperature units are Celsius. So you can change this one and work on it. And here, as you can see, if I go to this variable information, I can define the unit for this one as well. For example, for T1, I can just click here, right click, and then this is temperature per Celsius. I can paste it here, and for this pressure also I can use the kilopascal, paste here, and then OK. So here we need to define the temperature and pressure that is in this problem is T1 and P1. So you can directly write the number 90, or you can assign to this parameter that we define here. Then if I just press on the solve button, then we will get this information, which this specific heat is 0.145. Here also you can define the unit for this specific heat by going here and then define this one. So you can find this value, cubic meter per kilogram, and press OK, and then OK, and again solve the problem, and you will see the unit also here. Then finally, at the end, we can go again to this function information, thermodynamic properties, and then find out your refrigerant. So I can find it here, R134a, and then here I can find out the enthalpy. So I can simply paste here, and this enthalpy will be pasted here. Just I need to change this temperature to T1 and P1, and then solve the problem. Press on the solve button and then solve the problem, and the enthalpy is 333.9. If to check this value with the reference table for this specific volume, which is 0.145, I can go here, and for this 90 degrees Celsius and this pressure 200 kilopascal, this is actually the specific heat, cubic meter per kilogram, which is 0.145, which is exactly the same as this value here. And for this enthalpy, it is 333.9 if I go here. So for this enthalpy, it is 333.9, which is exactly the same as this table that we are going to check here. Here for this unit also we can define this kilojoule per kilogram. Here again I can go here and then define for the H here. So that's a kilojoule per kilogram, as you can see here. I can simply define it here in the EES software and then paste, and okay, so solve one more time, and then all these actually units are specified here, and we reach to the exact value according to the reference table. So that's it all for today, and we find out how we can find the superheat region for a given data in this specific example. And in the next video we can go and find out how we can determine the actually thermodynamic phase of a refrigerant if it is in the saturated region. So that's it for today, and thanks for watching.